Our session will be starting soon. This session will be recorded so that you can come back to it later if you need, and so that others who may have missed out on today's event will be able to come back and watch it. And so now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we will be sharing. If you're here for the Math 1324, we're going to be posting the room link on the chat so that you may connect to the Math 1324. We'll also be sending individual messages to everyone so that we can gather your students' ID numbers to sign you in. And now, without further ado, I'll pass it on to our presenters so that they may begin.
Good morning, everyone, and thank you for our happy math hour today. I do want to clarify today we are going to be together. Okay, so there's only going to be one. So if you're here for both the Math 1314 and the Math 1324, we'll go ahead and stay all together. Okay, and we're covering similar topics that are on both classes. So that's why we will be staying together. So again, thank you for joining us. Okay, so don't click on that link. Go ahead and stay here with us. Um, so again, today we plan to cover the functions, evaluating functions, domain, and the difference quotient. So let's go ahead and get started. So first, let's review what a function is. So a function is some set of rules that correspond between two quantities. These are called the relationships between um, two quantities, and the relationship is a set of ordered pairs. Okay, now the set of ordered pairs, um, we have what's called a relationship that is the domain, and we have a relationship that is the range. Now, the domain, what I tell the students is refers to all the x values in our ordered pair, and the range is the all the y values that correspond to our ordered pairs. Okay. So the definition, your book definition of a function is a function f from a set A to set B is a relationship that assigns to each element x in the set A exactly one element in y in the set B. Okay, so for instance, in this particular problem, it says find the domain and range. So here, the domain refers to all the x values of the ordered pair. So my domain here would be the 1, 3, and 5. The range would be all the y values from the ordered pair, which would be 2, 4, and 6. Okay, and as far as to keep in mind the definition of a function, okay, for instance, my x value here cannot have two different y values. So for instance, the 1 has only corresponds to the 2, the 3 only corresponds to the 4, the 5 only corresponds to the 6. So the 1 can have multiple values of y's. Okay, same with the 3 or same with the 5. So again, one way we can determine whether a relationship is a function is again by making sure that every x value corresponds to only one y value. So let's look here at our examples for A, B, C, and D. Okay, so for an A, they tell me that my domain here is 1, 2, and 3. Okay, these are my x values. My y values, based on this relationship, are the range, which would be 0, -8, and 6. See, these x values correspond to only one y value. Okay, so if we look at figure 2, okay, we have the same representation. We have a domain, and our x values here would be 8, 7, 2, and -4. And our y values that are corresponding to this relationship would be 5, 9, -3, and 5. Okay. Now, if we look at, so for instance, again, I was going ahead and I know that the answers are here for the solution. So for instance, does each element in set A correspond to only one element in set B? So again, in A, I said it is a function. Okay, same way with B. B is a function. But let's look at C here. C here says that I have a 7 is the y value represented to the 30. -5 is also represented to the 30. And 6 is also represented to the 30. And 8 is also represented to the 30. And most students would say, no, this is not a function. But in fact, it is also a function, because what this is saying is that each x value corresponds to its y value. The fact that they are sharing the y value means that these are all individual x values. Okay, so in this particular problem, c is also a function, because again, every x value corresponds to its y value. The fact that it's 30, it doesn't change the fact that I'm dealing with different x values. Now, D is a different case. If you see here on D, it says that 8 sometimes can be 7 and 8 sometimes can be -5. That we cannot have. We can't have one x value be equal to different y values. So again, in our D section, D fails. This is not a function. So again, when we're dealing with this relationship, which is a function, we got to keep in mind that every x value corresponds to only one y value. Okay. All right. So let's look at these as a set. Determine whether each relationship is a function. So we're looking at A. A gives us the ordered pairs 1, 2, 3, 4, 5, 6. And again, as we covered in our first session, ordered pairs, means that these numbers have an x and y value, and we always the x is first and then the y. Yeah, so we have 1, 2 for our first ordered pair, 3, 4, and 5, 6. So for instance, for A is a solution which would be a function, because every x value corresponds to only one y value. Okay. How about B? Here, if we have B here says 4 is equal to 0, which is fine. 5 corresponds to 10. 7 corresponds to 8. And 6 corresponds to 10. Again, the fact that the 5 and 6 share the y value of 10, it's okay. It's still satisfying my definition condition that every x value corresponds to only one y value. So 5, it's its own um, entity, and 6 is its own entity. Again, it's its own different x values. They correspond to the same y value. That is okay. Now let's look at C. And again, C, if we see the shortcuts, the domain does not repeat, then it will be a function. Okay. Again, -5, 1, 4, and 2. We don't have any repeating x values. So hence, we know that this is going to represent a fraction. That's what we mean our shortcut. We're looking at all the x values. Do we see that -5 repeated as an x value with a different y? The answer is no. So we know that this is a function. Okay. All right. So again, this is what I was talking about. I have -5, 1, 4, and 2. Okay. Now, function or not a function. Let me give you guys a couple of seconds here to look at this and see if you can use my shortcut way to discover if this is a function or not. Okay. And if we see here, we know that this is not a function, because on my shortcut way, what do we notice? We notice that we have two x values, a -1 here and negative value there. So that's a red flag. If this would have been a function, -1 has to correspond to only one y value, and it's not. It's telling me that -1 sometimes is 9 and -1 sometimes is 30. We cannot have that. The domain is repeated, therefore it's not a function. Okay. Hopefully we can easily see these, right? All right. Now, we can turn into visually determining whether a graph is a representation of a function or not. And the best way to determine whether a graph is a function or not is by performing what's called the vertical line test. Now, the vertical line test states this, that we'll use this imaginary vertical line and we're going to traverse it to our graph, okay? And if my imaginary line, okay, crosses the graph only once, then that means that every x value only corresponds to only one y value. So if we look at the first graph here on the left, and I do my imaginary vertical line, what I notice here is that my imaginary vertical line is going to cross my graph at two places. And what this is saying that it's telling me that for this x value here, I have one y value, and then I have a different y value over here. So again, it fails this test, and it's failing the definition of what a function is, that every x value corresponds to only one y value. So that first one is not a function. But what about the second one? Again, if I were to do my imaginary vertical line, and again, I traverse it across my graph, I would see that my imaginary vertical line would only cross my graph only once. So what that is saying is that it's satisfying my definition of a function, that every x value corresponds to only one value in the graph, so hence it is a function. Now, if we look at the last one again, we can see that it's going to fail the vertical line test. Here at this point, whatever x point value is, it's saying that at this x value, it could be either this y value here on the top or this y value here at the bottom. So I have two different y values for the same x value. Hence, this graph is not a function. Okay. So again, this is a great way to visually see graphs whether and determine whether the graph is a representation of a function or not. Okay. All right. Now let's look at this other set of equations. Yes, we are looking at equations. Determine which each equation represents y as a function of x. So we want to see if y is representation of a function of x. So let's look at the first one, a. Okay. So here, one way to solve this is again by graphs, and another way we can do it is also algebraically. So first, let's look at so again, let me pull out my pen and really just um, show you how we can represent these as functions. Oh, I keep double clicking on that. So in the first one, hopefully by now we've seen that and we've studied that this is an equation of a line. Okay, so if I were to graph this visually, all right, no worries, Miss Chuka, no worries. We'll just draw it here. Okay. Um, so if here on this one, it tells me that I have a y-intercept at 8. So I have 1, 2, 3, 4, 5, 6, 7. Let's say that this portion here is 8. So it's crossing the y-axis here. And then my slope is 1. So let me choose another color. If I can change the other color. All right. I'm having difficulties, but here, my slope is 1, so I'm going to rise 1, run 1. So here, oops, I lost my line again. Okay, there we go. Oops. Now this should be a straight line. I'm using my mouse to draw, okay? So if I see here, if I were to do my imaginary vertical line here, this graph would cross my graph only once. So one of the things that I can tell you is basically all lines can be represented as functions. There's only one line that cannot be represented as a function, and that would be a vertical line, because again, it would fail my vertical line test. But basically all lines are functions. So if I'm looking at this first one again, this one's a function. So let's go ahead and clear my board here. Let me see. There we go. Thank you. All right, so if we look at the other one again, we could do a table to graph this, okay? And I'm gonna do this just quickly, just because again, for our limited of time, but I'm gonna convert this equation. I'm gonna convert b into, why am I keep getting my old graph? Let me draw my x-axis here. But I'm going to convert this equation. Y is equal to, just for me, I'm going to put it like this. 4x squared plus 36. Okay. Now, if I were to graph this, okay, I know that this graph is going to be something along, yes, Thank you. So I am going to have a y-intercept of 36 and perfect. I have a parabola like that, yes. Okay, now again, if I do my imaginary vertical line here, I would see, just like on the previous examples, my imaginary vertical line is going to cross my graph only once. So hence, b is also a function. Okay, now, but if I do c with respect to y, this one's not going to produce a function because what's going to happen is I'm going to get a graph like this. It's going to be here is at 4, and I'm going to have a graph like this. Okay, so again, if I do my imaginary vertical line, it's going to fail my vertical line test. And then this one is just like on the example before. This equation here is going to produce a circle. Okay, and if I do my imaginary vertical line, it's going to fail my vertical line test. Okay. All right. So let's move on. So evaluating functions. So basically, the way you evaluate functions is, again, I like to tell my students that the x values, okay, of the function are my input values, okay, and that's what I'm going to place into my function. The output is, again, the y values, okay. So let's look at these problems. They gave me a function here, given the way we read this is f of x. Now, please, this is just a name. This is the most common name that we give functions, but this is telling me that I'm dealing with a function, and we like to use the letter f. This is the most common name, that my input values or my domain are the x values, and that when I evaluate this function, the output or what's going to come out are my y values. Okay, so again, this is just a name, and we'll change these. Sometimes the most common names we'll use in both classes is uh, f of x, but we can also use g of x, um, h of x are one of the couple more common ones. But again, this is just a name. So let's do the first one, a. A says at x equals 2. So the way I do it here is I replace x with the value 2 everywhere I see it. Again, I want to evaluate the function at 2. So what this is saying is that everywhere I see x also on the equation here part, I replace it with 2. Okay, and then I just simplify. I go ahead and do the operation. 3 times 2 is 6. 6 minus 2 is 4. And the square root of 4 is 2. So again, evaluating functions, x is your input value, and what's going to come out is your y value, okay? So let's do it again. Let's do b. B, they said x is equal to a. Um, so I'm evaluating the function at a. So everywhere I see x, I'm going to plug in a. Again, so 3 times a is just 3a, and 3a minus 2 is just 3a minus 2. So the answer for this one just stays as is. The square root of 3a minus 2, because again, a is a variable that can be anything. Okay. All right, and then the last one. Okay, the last one, it wants me to evaluate when x is equal to 6 plus h. Okay, so I replace x with 6 plus h. Everywhere I see it in the equation, I'm going to replace x with a 6 plus h. So here we go. So on this particular one, we have to do a little bit of our distribution property, where this 3 has to be multiplied with the 6, has to be multiplied with the h. Okay, every element inside that parentheses. So I'm going to get 3 times 6 is 18. 3 times h is 3h. We have that minus 2. So we want to combine like terms. So we have two constant terms that are just numbers so that we can combine them. So 18 minus 2 is 16. So the answer for evaluating the function at x equals 6 plus h is just going to be the square root of 16 plus 3h. Okay, and this would be my y value that comes out. Okay, all right, now let's look at another type of function, okay, that we want to review. And this function, again, it might look a little bit weird, but we call this function, this type of function, it's called a piecewise function. And the reason why it's called that way is because this function is determined or evaluated by two different pieces of two functions. It's like I like to tell myself, like a Frankenstein. It was two functions put together to evaluate. Okay. Now, So if you see here, the first function here is I know that I can recognize that is a line, okay? And then this one is something different, okay? And this one I don't want to give any clues, but we will deal with this one later on, a specific one. But this is a different type of function. Now, this piece here on this side tells me the restriction on my domain. And again, what is the domain? Is the x values that the graph can take. So on this particular problem, when evaluating this function, this first part of the function is only valid for values of x that are less than -1. So if they ever give me any value that is less than -1 to evaluate, I'm going to use this first part of the equation. But for the second equation, for the domain, I have a restriction. I only interested on all the x values that are greater than or equal to -1. So if they give me -1 or any value greater than -1, I need to evaluate the function using this piece of the function. Okay, so let's get to it. Now, evaluate the function at -4. So I say to myself, is -4 smaller than -1? The answer is yes, because if I were to apply it to the second one, -4 is not greater than or equal to -1. It's not valid for this one. So to evaluate this function, it's only valid for this function, okay? So when doing piecewise functions, like please keep in mind, you're only going to get one answer. Don't evaluate it twice, okay? Piecewise functions only give you one answer. So again, this -4 only applies to the first one. So I said, which function will it use? Again, it's the first one. So I am evaluating this. Individual function f of x is equal to -2x minus 2. Everywhere I see x, I'm going to plug in at -4. So here I have -2 times the -4. A negative times the negative is going to give me a positive. 2 times 4 is 8, leaving me with a -2. So 8 minus 2 is 6. So the value or the evaluation of a at f equals -4 is 6. That's my y value. Okay, let's do b. If they want me to evaluate the function at -1, then again, I'm going to say to myself, which does this function belong to? Then I pick the first one. Is -1 less than -1? No. It would be equal, not less than. So it matches the second one. Is -1 greater than or equal to -1? The answer is yes. So I am using now the second function to evaluate. So I write it out. F of x is equal to x to the second power plus 2x minus 1. That's the individual function. And everywhere I see x, again, I am going to replace it with the -1. So I am -1 squared is a positive 1. 2 times the -1 is a -2 minus 1. So 1 minus 2 is a -1. -1 with a -1 is a -2. This is my y value result from this x input evaluation. Okay, and let's do the last one. I want to evaluate the function at 1. So is again, ask myself, is 1 less than -1? No, that is a false statement. Is 1 greater than or equal to -1? That is a true statement. 1 is bigger than -1. So again, the function that I'm using again is the second one, the x squared plus 2x minus 1. Again, everywhere I see x, I'm going to plug in that 1. So we have 1 squared is 1. 2 times 1 is 2 minus 1. So we have 1 plus 2 is 3. 3 minus 1 is 2. So the y value that comes out from this function is 2. Okay, so this is an example of our piecewise functions. Okay, so now let's move on to another piece of problems. And what we'll be doing is the difference quotient. Okay, and the difference quotient you'll see if you move on into your math careers, you'll see this more in detail. But for us, we're using it to practice our algebra and practicing evaluating functions. Okay, so the difference quotient is a definition of a formula. Okay, and again, as I mentioned to you, it's one of our basic definitions that if you all get to calculus, it's a way to find ratios, and in calculus, it's used a lot. Okay, but again, for our purposes, we're going to use it to practice our algebra. So this ratio again is called the difference quotient and is given by these two functions, f of x plus h subtracted by f of x, all divided by h. And again, this symbol over here, h not equal 0, that means that h cannot be 0 because we're dealing with a ratio or a fraction. If we ever had 0 on the bottom, it would be undefined. So when dealing with a difference quotient, h is never 0. And that's what this little piece of information is telling us, that we're never going to get an undefined function for this difference quotient. Okay. All right, so it says evaluating the difference quotient. So I want to evaluate the function f of x is equal to 3x plus 1, and I want to find the difference quotient given by this formula. Okay, so let's go ahead and do it. I like to do it in pieces, so or break it up into three parts. First, I want to evaluate the first function, f of x plus h. Then I like to evaluate the function at f of x. And then the third part is just plugging everything together and simplifying. Okay, I feel that this is the best way to practice the difference quotient and evaluating the difference quotient. All right, so let's do the first part. I want to evaluate the function of f of x at x plus h. So again, the function that they're giving me is 3x plus 1. So the first thing I do is everywhere I see x, I'm going to substitute it with the x plus h. So I have 3x plus h plus 1. Again, simplify by doing the distribution property. 3 times x is 3x, 3 times h is 3h plus 1. Okay, I can't combine any like terms because they're all different. So that is it. I am done with that part. Okay. So let's go ahead now and do the second part. Evaluate the function of f of x by replacing everywhere I see x with x. But I don't have to do any work because I already have an x there. So it's just 3x plus 1. There was no work for me to do. So now let's combine everything together. Again, let's see. I substituted for x and I didn't have to do anything. It's already there. Okay, so I have these two parts. The part 1 is in blue. My part 2 is in green. Let's put it together. Okay, I'm putting it to the formula given for the difference quotient. So again, my first part, the f of x plus h was the blue one, 3x plus 3h plus 1, minus the f of x, which was in green, 3x plus 1 divided by h, or over h. Okay, so again, before I can simplify, I have to take care of the subtraction because I have a parentheses with two terms. I had to distribute that sign. Okay, so when I distribute that sign, a negative times a positive 3x is a negative 3x. A negative times a positive 1 is going to give me a negative 1. So once I've done that, I can see I look at my my part and I see if I can combine like terms, and the answer is yes. Okay, I see that 3x minus 3x will eliminate it, become 0. And then I also can combine two like terms, my constants. I have a plus 1 with a minus 1. So 1 minus 1 is 0. That got eliminated. So I'm only left over with the 3h divided by h. And I can see that this h can be divisible by this h, becomes 1. So my final answer is just 3. So again, this is a way for us just to practice evaluating functions with this very neat formula, which is called the difference quotient. Okay, so let's try the difference quotient again. Just let's look at this other function given. It says f of x is equal to x squared minus 4x plus 7. Find the difference quotient. So again, let's break it up into three parts. Okay, let's first do the first part, the f of x plus h. Again, everywhere I see x, I'm going to plug in x plus h. So we have x plus h squared minus 4 times x plus h plus 7. So the first one here, it's going to involve us to do a little bit of FOIL because x plus h squared means I have two of these guys. I have x plus h times x plus h. The second one was just a distribution. I distributed the negative 4 into the x, which gave me negative 4x. The negative 4 times the positive h gives me negative 4h. And I have this plus 7. But again, I go back to this first one here that I had two of them. Again, I have to do FOIL. This x has to be multiplied with this first one has to be multiplied with the outer one. This h has to be multiplied with this first one and to this last one. Yes? So let's go ahead and do that. So after doing FOIL, we have x squared plus xh plus xh plus h squared. We can combine these two like terms. So it's going to give us x squared plus 2xh plus h squared with the remaining of the function, which was the minus 4x minus 4h plus 7. And you always want to see, can I combine any more like terms? So the answer is no. I don't have any terms that are alike that I can combine. So I am done with that first part. So now let's move on to the second part. The second part, I'm giving x squared minus 4x plus 7, and it says replace every x value with the value x. And in this case, I already have the value x, so I don't do anything. It stays the same. It's just x squared minus 4x plus 7, again in green. Third part is let's go ahead and put everything together. Here we go. We have our blue part minus our green part divided by h. Okay. First thing I need to do before I can start combining like terms is distribute this negative sign now to 3 terms. Okay. So let's go ahead and do that. So a negative times a positive x squared, it's going to give me a negative x squared. A negative with a negative is going to give me a positive 4x. And a negative times a positive 7 is going to give me a negative 7. Now, can I combine like terms? Let's see. So the answer is yes. I have an x squared with a negative x squared. That's going to give me 0, or that cancels out. I have a negative 4x with a positive 4x. When I add those two or combine those two terms, that gives me 0, or that cancels out. And then I have a plus 7 with a minus 7. Combining those two like terms is going to give me 0, or again, this cancels out. And I grab what's ever left over. So what I have left over is I have a minus 2xh plus h squared minus 4h. Now, what I tell my students is several ways of simplifying this. Let me see. One way, and the way that I like to do it, is by factoring out the numerator with that common h that all those 3 terms have. So you see the first term had an h, the second term has 2 h's, and the third term has an h. If I factor that out, I'm left with minus 2x plus h minus 4. And the reason why I like to factor it out is now I can see that h divided by h is going to give me 1. And I know my students like to say that they cancel out, but it becomes 1, and it gives me the final answer. The final answer is just left with minus 2x plus h minus 4. Okay, so again, this is a way of evaluating the difference quotient. Again, it's helping us practice the evaluation and our algebra. Okay. All right, so again, this would be my answer. All right, so let me go ahead and pass it over to Ms. Chuka, and she'll tell us all about the rest.
All right, thank you, Ruben. So now we're gonna talk about domain. And domain is a very important topic throughout any of your math classes. And so hopefully this will help you. So the domain, as Mr. Carizales mentioned earlier with some of his examples, are all the x values that we see. And we usually use the variable x, but it could be the variable t, for example. But the domain is everything that is on this axis, whether we call it x values or the t values, but it's going to be all of these values here. Now the domain is any number that can be used to help you create this graph. So for example, if I pick this x value of 5, if I go up, it's actually going to be part of my graph. Okay, so if it helps you create the graph, then it's going to be part of your domain. Now let me go back. The range is going to be something that you're also going to be looking at. Let me draw it in a different color. So the range is going to be all the y values that we're using to make this graph. So for example, 10 is part of your range because it's used to create the graph. Now, when you're not given a graph, it makes it a little bit harder to identify the domain. And so one of the things that you can do is ask yourself, in your equation, does it have a fraction? And does that fraction have a denominator? In your denominator, does it have a variable? If it does, then that means that you're going to have a restriction. Okay. The second thing you want to consider is, does my equation have any square roots or even roots? And if it does, then there's also going to be restrictions. And those restrictions are going to be any numbers that are causing our radicand, which is the inside of the square root, to be negative. And then the third part, which is going to be something you see later on in the semester, is if you have any logarithms. If you have logarithms, then you'll have restrictions. But if you could say no to these three questions, then your domain's always going to be negative infinity to positive infinity. So let's try some examples. So here on the first one, we have y is equal to x plus 5. And so one of the first things you want to ask yourself is, does this equation have a fraction with a variable in the denominator? And the answer is no. The second thing you want to ask yourself is, does this equation have a square root? And the answer is no. And so we can say no to that. And then the third question is, does the equation have a logarithm? And if it has a logarithm, it's going to have the word log on it. And as we can see here, it doesn't. And so since we're able to say no to these three questions, then our domain is going to be negative infinity to positive infinity. And if I was to sketch the graph, then you can see, let me get my pen. If I was to sketch the graph, then this is just a line that goes like this. Then this is just a line that goes like this. And you can see here that we're using all these x values. And that's why we're going to say negative infinity to positive infinity. And right now, this is written in interval notation. So let's try another one. So for the next graph, you want to ask yourself the same question. Does this have a fraction? And give me a second. Let me plug in my computer really quick. Does it have a fraction? So the answer is no. Does it have a square root? And the answer is no. Now, sometimes we might confuse the square root. We might confuse the square root for the square, but they're not the same. Okay, so we want to be careful with that, but there's no square roots. And the last question is, does this have a logarithm? And so there's no logarithm. Because we're able to say no to the three questions, then we can say that our domain is negative infinity to positive infinity. Let's try another one. Okay, and then there's the graph in case you want to see what it looks like. And again, you can see that we're using all the x values here to make this graph. Okay. Now the next one, find the domain for y equals 1 divided by x plus 4. So our first question is, if we have a fraction with a denominator, a variable in the denominator, and the answer is yes. So as you can see here, we have x in our denominator. So here we cannot have the number 0 in our denominator because we can't divide by zero. Therefore, what we can do is take our denominator and set it equal to 0. And in this case, we just get 0. We want to solve for x, which we already did. And so what this tells us is that the domain can be any number except for x equals 0. And the reason is because we cannot divide by 0. Okay. So to write our domain, we're going to say that our domain is going to be everything except for 0. And how would we write this in our interval notation? From negative infinity to 0, union from 0 to infinity. And here we use parentheses for infinity because that number is not included. So basically what happens is you have your number line, and you can use all of these numbers except for 0. Okay, so that's what this represents here. So let's try a different one. For letter B, y equals 4 plus 3 divided by x minus 6. Is there a fraction with a variable in the denominator? Yes. So that should ring bells. That's has exception or restrictions. And to find those restrictions, we're going to set the denominator equal to 0 and solve for x. So in this case, x cannot be 6. So we're going to exclude our 6. And so our domain is going to go from negative infinity to positive 6. And then the symbol, this U symbol means union, which means to include everything together. And then from 6 to infinity. Okay, and you can see the graphs here for each of these functions. Okay, so let's try this one. Do we have a fraction with a variable in the denominator? No. And so the second question, do we have a square root? Yes. Since you have a square root, then you have restrictions. And those restrictions, you want to make sure that inside of the radicand, which is the number inside, has to be positive. Okay, because we cannot take the square root of a negative number, for example. So to figure out what those restrictions are, we can set the radicand, which is a number inside, greater than or equal to 0, and solve for x. So here, for this answer, that's where your domain is going to begin. And since we have the equal sign here, we're going to start by using a bracket because we are going to include that number. So this is going to start at 0, and it's going to go to infinity. Okay. And the graph, I don't have the graph, but let me draw it really quick. So the graph looks like this. And so as you can see here, all these x values are being used. But anything that is over here is not being used to create that graph. So for letter B, we want to set the radicand greater than or equal to 0. We're going to subtract 5. So my domain is going to start at -5 to infinity. Okay, and I guess I did have the graph. And so here we can see the graph and where the domain starts and where it goes to. So now what we are going to do is combine what we just did with a little bit different evaluating functions with the graph. So here it says use the graph to find the domain and range and then the indicated values. And so first we'll work on the domain. So the question you want to ask yourself is what x values are being used in order to graph this equation. And so we can see here, for example, these x values are not being used and these are not being used, so they're not going to be part of our domain. So the first x value that is being used is right here. But notice that in this point, it's an open circle. So if you have an open circle, it means that we're not going to include that point. And then it goes all the way to, so all of these values are being used all the way to this point here. So the way we can write our domain is going to go from -2, which is right here, all the way to +2. And I use a bracket on my, I use a bracket right here since I'm not including this -2. And then I use a, I use a parenthesis because I'm not including it. And then I use a bracket since I have a closed dot. Okay, now the range, we're going to look at the y values. So you always want to write your smallest value first. And so you're going to have from -4, which is right here, all the way till we get to 5. And I'm going to use brackets on both because these points for y are being used to create the graph. Okay, so now for the next part, we want to know what is f of -1. Remember that in the parentheses, that -1 is representing our x value. And so we want to know what do we get when x is equal to -1. So here's -1. If I go down, then I get to -4. Okay, and then for 0, if I go down, then I reach -3. And then for f of 1, if I go down, I reach -4. And then f of 2 is going to be 5. Okay, so that's how we would evaluate these functions with the graph. Let's try another one here. So for the domain, what x values are being used. So again, basically what values are being used to create this graph. So all of these are being used all the way to this point. And then we still use all of these. And so it looks like our domain is going to be -infinity to +infinity. Now for the range, the smallest value where we begin is at -2. And then we use all of these numbers going up are being used to create the graph. But notice that at -2, we have an open circle. So that tells me to use a parentheses because we're not going to include -2. And then it's going to go all the way to the top. So one of the questions might be, well, why have -2 if we can't use it? And the reason is you want to get all these points that are right here close to -2 that we really can't see them, and there's an infinite amount of them. And so if we just include -2 with the parentheses, it's going to capture everything above it. Okay, so now let's try f of 2. So I go to x equals 2 and figure out what the y value is. In this case, my y value is 0. F of 1, my y value, is it going to be -2 or is it going to be 0? So again, the open circle tells me that I'm not using that. And so my y value is going to be 0. And then f of 3 is right here. So if I go up, I check to see what my y value is. And that's going to be 2. And then f of -1, we go up. My y value is going to be at 2. Okay. And we have another one here. Now we're going to look at increasing, decreasing, or constant. We want to know when is this graph increasing and decreasing. You want to go from left to right. Okay. So if we're going from left to right this way, then we can see that the graph is decreasing at this from here, and then it starts to increase. So we want to know when does this happen, on what interval. So let me just put some arrows here because this graph is going on forever. So as we're coming from left to right, we can see that this graph is decreasing all the way until we get to number 6. So let me just do this here. So all of this part of the graph is decreasing, and the interval is going to be all these numbers here, which we can call -infinity. And then it stops at 6. At 6, it starts to increase. So I'm going to put 6 here. And then from 6 all the way over here, the graph is increasing. So from 6 to infinity, the graph is increasing. So from 6 to infinity. And there's no constant part. And so we always use parentheses because we are only identifying the intervals. And so as I mentioned earlier, this part is decreasing and it's from left to right. So this area is decreasing, and then we can write it, and then we have the increasing part. And then you can see we can write it as 6 to infinity, -infinity to 6, and then the constant does not exist. So we'll try one more. Let me go ahead and draw the arrows since this is going to continue here. Okay. So now this graph from left to right. So this graph right here is decreasing, and then it's increasing over here. But we need to identify where that's happening. Okay, so it's decreasing from all of these points until it gets here. And then let's see, oops, I didn't mean to do that. So here's a decreasing, decreasing, increasing. And then our increasing goes from 5, which is here, to infinity. And our decreasing is from negative, which is all these values right here, negative to -5, and then increasing from 5 to infinity. And there's no constant part. Okay, so hopefully that gives you an idea for 1314. These are some of the problems from section 1.4 and a little bit of 1.5, and 1324. This is also the domain and evaluating functions is what was covered this week in your classes. And so every week we're going to be covering what we have on the calendar. And so, for example, next week we might separate already. And so that way we can focus more on each class. But I'm going to go ahead and pass it back over to our friendly staff.
Next week, we will have combined Math 1314 and Math 1324, and the topic is factory, column, review different factoring methods. Okay, thank you so much to Professor Iwatsuka for presenting today. Thank you to the audience for coming and being a wonderful audience, and hope to see you again soon. Thank you.